Assalamualaikum warahmatullahi and very good morning. I am Nasiruddin from USM. I'm here to present my topics on nonlinear control in uncertain dynamical systems in the era of Industry 4.0. So a little bit of myself. I am with the School of Electrical Electronics Engineering. I did my PhD in 2014 with University of Bristol on nonlinear control and robotics. And I was appointed as a visiting fellow with the same university for 4 years. And recently, I was appointed as a project lead for an international grant for robotic and AI in nuclear research, which is hosted by University of Manchester. So I had some application engineer experience with Asian technologies. Okay, so here's my specialization. So basically, I did my research in adaptive control, nonlinear control, and I venture my research on cooperative control. So these two areas are my topic of interest. And for today's talk, I would like to discuss mainly on two types of system. First is actually a single dynamical system, nonlinear control, and second is on a cooperative system. So before I begin the main technical talk, I would like to share with all of you on some bits of motivation about control theory or technologies. So as you know, in the control is one of the driving technology in Industry 4.0. As with the case of smart factory, all these components such as monitoring tool, instrument, sensor, HMI, robots are essential. And control system is one of them. And control is often regarded as a hidden technology as it operates in the background of a dynamical system. So let's look at the modern factory. So we can see that we have a mobile robot, independent robot doing the warehouse safekeeping. And we have a specialist robot that does welding, painting, and handling materials. So as you can see clearly that the human workers need to stand at a safe distance. So as a robot technology evolves, the human can stand closer to the robotic arm because they have been equipped with some bits of compliance feature. And as you can see here, at the end, we see a Baxter. So Baxter is actually a meant for cobots or collaborative robot created by Rodney Brooks. So this particular special robot is capable of self-learning feature. And in a nutshell, in context of control, when we want to control a robotic arm, we have to deal with unknown dynamics, unknown disturbance, unknown environment interactions. And in context of a collaborative robot or cobots, we need to deal with the human interaction. Therefore, uncertain dynamic information need to be known or estimated when designing a suitable controller. So we talk about, on the top left, a cooperative robot. As you can see here, we have a two robotic arm trying to synchronize motion in the pursuit to balance a cup of water. And on the top right, whereby you see a Baxter that is capable of self-learning, but then the dynamics remain unknown. And we have also a case where a robot is deployed or commissioned to do some task that is remotely challenging environment. When I talk about remotely challenging environment, is an environment whereby the human cannot go in. Environments such as nuclear, environments such as very hazardous environment. So this part where the robot is deployed, but then it is very important that they need to be controlled. And the control strategy requires this dynamic to be estimated. And in the bottom left, in context of social robotics, whereby human-robot interaction involved, so the dynamics, there's so many uncertain dynamics need to be known when designing a controller. So in a summary, uncertain dynamics can be classified into three parts. First is unknown or partially known system parameter information. Second is unknown disturbance. And third is unknown nature of environment or external interactions. So this is actually referring to human-robot interactions or an interaction whereby the robotic arm need to actually engage a task that involve objects externally. So how do we deal with uncertain dynamics in control? So there are several methods actually to mitigate uncertain dynamics. These are actually commonly known by most of the control scientists, control engineers, for example, like linear control, whereby it is meant to work within the linear operating region. And in the case of model-based nonlinear feedback compensation, we talk about model reference or indirect adaptive control, whereby there are many types of adaptive law can be used to estimate parametric information. And we have a robust control here, such as sliding mode control or super twisted control, which works by strongly force the system to comply to a sliding manifold, for example, and they adopt the philosophy, the design philosophy, whereby the parametric informations are not need to be known, because they use a strong signal to reject all these uncertainties. And lastly, we have a model-free control, which does not require the parametric information, but rather requires only input and output signal of the system. So knowing that with a limited amount of time in this talk, I will just focus on the model-free control. A little bit of philosophy. As you can see here, this is actually a football field of a USM. So it's very green. You can see there's so many trees here. I would like to share with you on the so-called Sejahtera concept in control. So literally it means peace, balance and prosperity. It means harmony and safe. So this definition is taken from this book, The Genesis of a Sustainable Campus in 2007 USM. So I like to borrow this concept in context of control. So we can actually achieve a balanced controller, or a controller that is harmonious with the dynamical system and environment. And most important of all, to ensure or guarantee a safe usage, we have a stable controller. So just a thought, can we formulate a controller that is harmonious in tracking performance without the adverse expense of control effort? And I would hypothetically suggest there is some kind of balance that exists between the control signal, dynamical system, and the inhibited environment. So can they be peacefully balanced? So the choice of control strategy depends on the class of a dynamical system and whether the system is mobile or stationary, and whether the environment, also depends on the environment in which the system inhabits. So therefore, in this particular talk, I will only cover for the class of a dynamic system. So let's actually look at this class of dynamical system, shall we? So here, as you can see, we have a first class of dynamic system, which is termed as multiple input, multiple output coupled system. So in this case, I give an example of robotic arms, which have been doing research for the past 10 years. So a MIMO coupled system is whereby each of these robotic arm, each joint you need to send torques. So therefore, the torques will create a motion to create some useful work. And the uncertain parameters can be, for example, unknown mass, unknown link length, and perhaps unknown friction. And we have another class of dynamical systems, just non-affine system. So this is actually a particular famous example, which is continuously stirred tank reactor, or in short, we call it CSTR plant. So this actually is a non-affine in terms of structure. We will look into it in a minute. And it has a highly nonlinear characteristics. And yet, most of the time, these parameters are unknown. There is a nominal information, but then, as you see, the parameters usually changes. And we have a chaotic system here. Later, we'll discuss this in depth. where this particular plant is very interesting in context of Industry 4.0, because usually this is used for fault detections. And the control engineers or control scientists only just try to try to control it, because it's a very unstable system. But if you're able to control it, we can make it into full use. And the fourth one is actually under-actuated system, such as drones, even for wheel mobile robot, and underwater vehicle. So due to the limited amount of time, I will just only review on a MIMO couple system and non-affine system. So let's look at the general structure of a robotic arm. So here we have a general structure of robot dynamics of n degree of freedom, and we have an inertial matrix, we have a Coriolis centrifugal, and we have a gravity and torque input. As you can see here, the torque input exists as it is, because the torque input actually we send a torque to each of the joints to create a motion, and this structure we call it as a affine system, because there's no any other coupling that couples to the control input. Okay, so that's fine. And we only use the normal adaptive control law paradigm. We use a nonlinear feedback compensation, whereby most of the time the mass matrix, Coriolis centrifugal, and the gravity are not known, and therefore they need to be estimated. Then you can use adaptive law that is available in the literature to reconstruct these unknown dynamic parameters online. Okay, it's not a big deal. And this part basically is a compensation part, and this part is actually a servo tracking part. But now, and further work can be referred to my publication. Now, that comes to questions. What about the non-affine system? Can we apply the same concept, i.e. nonlinear feedback compensation, to a non-affine system? In this particular case, to deal with the uncertain dynamics in the CSTR plant? The answer is no, it will not work. For a CSTR plant, because it has a non-affine structure, as we see in a minute, that it is heavily nonlinear. As you can see, this is actually a model, a differential equation. So you have a state equation, that a state variable that is actually a concentration and temperature. So this refers to a state. We would like to control the concentration of the mixture as well as the temperature. And there are several ways of you control it. It's either you control the temperature of the coolant that goes into this coolant jacket, or you control the flow rate. So most of the time, even in industry, they choose to control the flow rate of the coolant because it's practically more feasible. But now there comes a challenging questions. If you look at this term, this is QC is a control input, and it appears in the exponent of exponential function. And this so-called QC is actually what we call the control input, and is coupled to the already existing heavy nonlinear. So it's very, we can term it as a nasty non-affine. So there are solutions to control this non-affine system. I would like to advise the audience to refer to my work, the recent work, because since there's a limited amount of time, I will just focus on a dynamical system of using a model free. So and let's look at this chaotic system and under-actuated system. So this is a chaotic oscillator. In this particular case, there's so many models. One of them that paid my interest is actually Duffin-Holmes oscillator. So a Duffin-Holmes oscillator is used to actually detect machine faults in industry, for example. So, but before it has been used or can be used for fault detection, they need to be controlled because they are very highly unstable. And later I will explain this plan in my main technical talk. And bear in mind that uncertainty also exists in a cooperative setup. For example, in the case of a leader-follower synchronization problem, whereby we have multiple manipulators are meant to synchronize to their leader manipulator, so they are interconnected by a graph, and they have a dynamics, for example, mass inertia, centrifugal, and gravity vector need to be dealt. So these are or can be estimated online and used for synchronization control. In the case of formation control, for the case of a under-actuated system of drones, so we want these drones to be actually form a certain geometric pattern, and the controller needs to know about their dynamics, and this need to be so-called uncertain dynamics can be estimated online. So further referral is advised to refer to the reference suggested. And uncertain dynamics also exists in the case of wireless sensor network. So we have a network of wireless sensor nodes, and they one particular problem that is actually still an open problem, but it is not. It has been solved with so many control techniques. And basically, the objective is to synchronize the reference clock, because each of these wireless sensor nodes have their own skew rate and offset. So these are unknown, and usually they depends on the crystal clock that they have, or the nonlinearity that exists in each of the crystal clock. So the time synchronization using control technology can be used to synchronize so that each of the nodes perceive the same reference clock. So we can use basically a consensus control to achieve this objective. Okay, let's move on to the technical part. So I'd like to discuss on the nonlinear control of a dynamical system. Let's talk about adaptive model-free control for a robotic manipulator. So we have a unknown nonlinear multiple input, multiple output function. So we have f of x of u. So as you can see, this is actually a undefined nonlinear dynamic system, and we can use we have system states of x, and A is also unknown. So A is a system matrix, Jacobian, and A basically is referred to the coupling between the system states. And U is actually a control signal that we would like to design using model-free approach. And we design it without having any information about the actual model of the plant. So A and F we would like to estimate online using input and output data. So we can use a mean value theorem to basically separate this term so that it becomes decoupled. So we have a nice control input term, and we have a nonlinear function G here, and we use an adaptive control to estimate the G and A. So we define the tracking error. So XD is a desired trajectory, and X is system states. So we generate a tracking error, and we have a zeta, which represent integral error. And by virtue of a model-free control policy, we combine the optimal term as well as a compensating term here. So if you look at the compensating term, you can see that the G hat here is actually an estimated nonlinear function, and A is an estimated system matrix. So this, we'll see in a minute that these two terms can be estimated online using adaptive control. So again, I'd like to revisit the Sejahtera concept in control. So again, we'd like to reflect how we can achieve this. So denote V as a function of a cost to go function. So we have a function of J that is comprised of tracking error and control effort. So we like to balance out, try to achieve some kind of an optimal solution that it achieve a tracking error at the same time with a minimal control effort. So using the Hamilton-Jacobi-Bellman, we like to minimize this function, and And this particular nonlinear function is reconstructed using the adaptive law, and we have a leakage term here to stabilize the adaptation. And then we have this, so online determinations of system metrics, and this is actually the usual Lyapunov function that is commonly found in the case of adaptive control. And this time, the linear term, which is unknown, is estimated online using some kind of a filtered versions which comprise of states. We use information of state system input and the estimated nonlinear function, estimated linear function. So this is actually from a W tilde, which forms to reconstruct the A. So this is simulation results. So this is actually a simple robotic manipulator. We like to control the tracking of joint angle, first and second. As you can see that it tracks really well, and the track is symptotically stable. With the case of estimation, as you know that uncertain dynamics can be estimated online with the case of this particular model. And for the linear term can be also estimated. So they are bounded. And you can see that the control signal U, which is the which is a top input to the robotic manipulator, is also bounded. And we have this P matrix is estimated online, and they are bounded too. Okay, so let's move on to the nonlinear control of a cooperative system. So just now we have looked at into a single dynamical system, a single multiple input, multiple output couple system. And now we shall shift to a cooperative system. So, and I would like to pay a special attention to a chaotic plan because this particular problem, which is a leader synchronization and formation control problem, I have already presented the work on these two types of cooperative system back in September 2017, which is a MACE technical talk at MMU. So I presented at that time the formation control of quadratos and leader-follower synchronization of multiple manipulators. So I've discussed this in depth, and but now in this technical talk today, let's look into this particular chaotic plan, and specifically speaking, we look at the Duffy-Holmes oscillator. So I'd like to present to you the model-free base cooperative control for a network of nonlinear agents. So here is actually a dynamic equation for Duffy-Holmes oscillator. According to the Brunowski form, it has a second-order system, and has a nasty nonlinear term here, and have a periodic term appearing here, and this is as you can see is a affine term because the control input is coupled with its own states. Okay, and we have each of the oscillators have their own states. So this particular chaotic plan is useful in detecting machine faults in the context of Industry 4.0. Place this oscillator in the several parts of machine, and due to, why is it so special that particular chaotic plan is sensitive to mixed signal, but it is immune to noise. In the control engineers, a certain set of control scientists paid special attention to this special feature. So we as a control engineer or control scientist, our task is to make this system stable. We can excite this oscillator to whatever frequency to match with the frequency of a mechanical system. And once it is stable, then we can pass this oscillator to the for example, test engineer or to instrumentation engineer, right? I've cast this problem in context of a cooperative system because, as you know, in context of Industry 4.0, we don't place one oscillator. We can place many oscillators, and we can make them to synchronize each other. So we can connect these oscillators in a network. It can be, well, I can name few, which is one of them is actually the fault detections, but they can be used for other applications as well. So the task for a control engineer like me, myself, I would like to synchronize the states so that they are in sync. And I write the dynamics of each of this oscillator in a affine system. So this actually have been transformed into an affine, and still we have G and A are unknown, or we call it uncertain. And then they need to synchronize to their virtual leader. So, and we write a consensus error or cooperative error. So this is actually the usual cooperative error. We have this leaders and we have this neighboring agents. And A actually defines the connectivity between agent I and J. So first, what is unique about cooperative system is that we can define the connectivity between this nonlinear system in a graph, and represent this graph in the form of a matrix. So what is interesting about this matrix is that, in particular, Laplacian matrix is that it has some unique feature, and you can use this unique analyze or to prove the convergence to prove whether it is stable or not. Again, we like to comply with the concept of Sejahtera concept in control. So let's look at this protocol. I can actually explain this in a much more simpler words. If you look at this decentralized controller, so H of I is actually the term or network term. Let's go back. So H actually contains information about network connectivity. So each of these agents has or know the information about the network connectivity, and they also know about the neighboring control input. I will show you in a minute how this the neighboring control input be reconstructed. But let's focus on this part first. In this protocol, it requires the control input of a leader. And like with the case of a single agent dynamics, it requires the nonlinear term, or we call it uncertain dynamics, and the linear term. So these two terms need to be constructed using the adaptive law. So this adaptive law for the unknown linear function is the same as what we have visited with the case of single dynamic system. But for a nonlinear function, you can see here that it used network information as part of the requirement to reconstruct the nonlinear function, and use the algebraic Riccati equations to actually update P using the estimated A. So Uj is required in Ui in this particular case, and Uj here at the bottom, Uj is actually a control input of a neighboring agent. So if you have oscillators in a network, so one oscillator requires information of the control input of a neighboring oscillators. And what is interesting about this cooperative control, you can actually estimate or anticipate the control input of the neighboring agent by having an observer that reconstruct using network information as well. So this is what is actually it's kind of like a beautiful way of signal reconstruction within a nonlinear control setup. So bear in mind that here there is an S here, which is a diagonal term. It's a diagonal term that goes diagonally, so they are decoupled. And we can suppose in the event that the states are a bit noisy, we can use the normal Kalman filter to actually clean up the states so that, for example, the reconstructed control input will not be noisy. So Kalman filter is hand in hand with the cooperative control here. Okay. And bear in mind that the UOM is only the bounds. So it does not require the control engineer to know definite information about control input of a leader, but at least the bounds of the bounds of the control input is known priori. So, okay, again, we have this heavily nonlinear chaotic system, which is Duffy-Holmes oscillator. And we like to actually, we have four of them, four Duffy-Holmes, and we like to synchronize to its leader. And we define adjacency matrix here in this manner. So they are connected, and the interconnectivity is defined by the adjacency matrix. And B is a pinning matrix. This is not a control input. The B is different from the B in this case. This B is a network-based pinning gain matrix. So all of this chaotic oscillator synchronize with its virtual leader, and the values and their states. Suppose if they are commanded to follow a certain harmonic signal, then they are allowed to actually they follow this despite of being nonlinear and non-affine in their dynamic structure. So as you can see that the control input is observed using the observer, is a cooperative observer. So all this is only one of the agents. And the nonlinear terms for G is also estimated online, and the estimation is bounded. Same with the case of system matrix A. They are also bounded too. So in a nutshell, this consensus problem is solved for the network of completely unknown dynamic system, or in the context of this talk, is uncertain dynamics. And then we use model-free controllers to actually define using regressive free. So we only utilize the input and output signals of a dynamical system. So we don't need, in the context of a data-driven approach nowadays, we can achieve this using a minimal signals. And all the gains are updated online at each agent. So these are some bits of my research work. Is a control of a complex system theory application. So in this chapter, I discuss on there's so many adaptive law that we can use, and one of the particular interests is that a finite time control, which is used for in a multiple output system, and also single input, single output system. Work to do with human-robot interactions, in particular, whereby cooperative control is merged with the robotic control, are discussed in this work. So bits of information about my ongoing research. I'm doing my research on the dual robotic arm for post-processing of nuclear decommissioning waste. So this is actually involving reactors for the it's actually a project hosted by University of Manchester. So in this particular project, the robotic arm need to be controlled to actually work in a glove box. So you need to do, so there's a glove box, and there is a so-called radioactive material need to be dismantled or decommissioned. And then, as you know, that this is a good example of where robots and control be used in the challenging environment setup. So this is still an ongoing project. So complying with the United Nations SDG 12.4.1. So it is actually focusing on the safe removal of the existing nuclear waste. So my other work currently doing is cooperative control of heterogeneous dynamical system, and I'm also continue to work on a model-free as well as model-based control. So again, borrowing from the Sejahtera concept, I would like to pose the questions whether can we achieve a harmonious nonlinear control, a paradigm, a beautiful paradigm in this era of Industry 4.0. So with this, I would like to say thank you.